All right, everyone, let's take a quick look at functions in C++. It's an interesting story on its own because there are really three different, quote, kinds of functions, even though, they're all functions. We'll see regular functions, lambda functions, and then we'll construct our own functions using the function call operator. And then we'll take a look at the actual types that each function has. All right, let's start with this simple little script. Let's draw let's make a little function right here. Let's start with a function that just adds 3 to its input. Okay, so return n plus 3. You've seen things like this in C++. The parameters come after the function name and the function return value comes before. I can make another little function that doesn't return anything, in which case we mark it void. Let's make a little function that will print integers. And we will just do the output over here and a new line, just to have something simple. And if we want to see our functions in action, we can call print, we can call add3, and we can run that, and hopefully we're going to see 8. And there we go, we do indeed see 8. Right now, functions are interesting because, sure, you can call them, but you can also pass them as functions too. So let's create a little function that calls a particular function twice. So the idea here is I want to call some function f on some integer n twice. In other words, I want to return f of n like so, in which case I might do something like down here, let's print the, let's call the add3 function twice, starting with, say, 13. So we'll say 13 plus 3 plus 3. And hopefully we'll end up with something like 19. But the question is, what's actually the type of the function f? Well, it turns out that we want to, if we're going to call a function on an integer and then return an integer, then the type of this is going to be a function that, okay, and here's where it gets interesting. It's a function that takes in an integer, and not with an arrow like in most other languages, like Go and Swift and Rust. You put the return type before the parameters. So a function that takes in an int and returns an int is written as function int like so. Now, add3 actually indeed has the type of function taking in an int and returning an int. So this thing should all look good, and calling add3 twice on 13 would be 13 plus 3, and then plus 3 again. We should get 19, which you can see we do. Okay. Now, what else can we do with these functions? We could get a little bit fancy and write functions that return functions as well. So let's write a function called compose. And compose is going to take in 2 functions, and it's going to return a function like so. All right, so let's do it like this. So we're going to say I want to return a function that returns an int from an int. And I'm going to call it compose, and compose is going to take in 2 functions like this. So we're going to take in a function called f, and we're going to do this whole thing again with g. And we're going to, now what are we going to do now? Well, we need to return a function that takes in an int returns. How are we going to write this function? Well, I don't know. Like I know how to return. Maybe if I return print, or if I returned add3, I mean that would be okay. Look, there's no errors right here because add3 is a function of intent. But we need to dynamically create this function. We basically want to return some function that returns f of g of x. Now, if this were JavaScript, we would just say f of g of x, and that would be interesting. But this is not the syntax in C++. In C++, dynamically constructed functions called lambdas have a syntax that looks something like this. Here's the parameters, and here's the output. So if our parameter is an integer x, And we would like to return f of g of x here. And we're almost writing pretty good C++ here, except you see we got errors around f and g. And it's talking about captured. So in C++, you don't automatically have access to f and g. It is required that you specify them directly as being captured or imported into the local scope. So if I brought in f and g like so, I'd be okay. And now it doesn't complain. So in this case, I can now create a new function. Well, in fact, let's do this. Let's make a function called add6, which is the composition of adding 3 and adding 3. This is not a very interesting function by any means, but it should work. Now, what's the type of add6 again? Yeah, it's function int, but you know, it's getting kind of tedious to write that. Let's see if, yeah, C++ can figure this out. That's pretty good. So let's see if we can print the add6 of 6 of 20, 21. I like to use Fibonacci numbers for some reason. This should give us 27. Let's see if it does. And it does. Okay, so yeah, we can compose functions too. This function is not actually very interesting, though. I mean, we just could have called the function twice. So let's get a little more interesting. Let's try to write a function that like add3 over here. Add3 always returns 3, but let's try to see if we can write a function that'll return add any value at all. So what if we just wrote a function called add some particular value n? And what I want to do here is return a function that will add n to its argument. So we're going to return a function that when taken, now n doesn't really go with anything, so maybe we'll use x and y instead. So let's write here a function that takes in a value y and returns x plus y. And yeah, we got a lot of semicolons are needed over here, aren't they? Now we don't have access implicitly to, also this needs to be a function from an int to an int. So we can write function int to int, or we can say just C++, figure it out for yourself. Again, we don't have direct access to x. We can specify it here directly. If we want to say import everything or capture everything, we could just use an equal sign right here and it would basically capture everything. Might look nice here because, you know, instead of capturing f and g, we could just capture equals, and that works too. I like to be a little bit more explicit and say, you know, just capture f and g if I can. Now we are getting an error here because, oh no more errors. This is good. So, all right, we now have this add function, which will add anything. So just like add3 always adds 3, I could write a function called add5, which would be, I'm going to call add of 5, and that's going to return me a function that adds 5 to its argument. What type should it be? Just say auto. That's easy. If I wanted to write function intent, I can do that too. Your call, intent, that also works. But what's really cool is to say print add 5 of, I don't know, let's just do 12, and let's see if we get 17, which we do. And this means that right here, to be more interesting than calling add 6, which is the composition of those two functions, let's compose add 3 and add 5. And this would be an add 8. And what's cool here is that add 3 is like a regular function, but add 5 is one of these lambda-ish functions that I get from just calling add with just one argument. I pass an argument, then I get back another argument. So add 8 of 21 should give us 29. Let's see if it does. Yes, it does. And, you know, if we wanted to do our add function directly, we could also say, let's add 3 and 8, and hopefully get 11, which we do. All right, so this is actually somewhat interesting because now I'm wondering, hey, what if I try to get fancy and just pass in a whole bunch of these these arguments like one at a time? Because you know what we're doing here, right? I'm sure you've probably seen stuff like this before. We call this thing currying when we pass in the arguments one at a time. And this, of course, allows us to build partial functions like add 5. And then we can just apply add 5 a little bit later. And that's all fun stuff. But then actually, how would we do something like create a function that can take an arbitrary number of arguments? Well, before we do that, I want to look at a third way of creating functions. And that is to just create an object with a method that overloads the function call operator. So I'm going to go in here and say struct. I'm going to make a little function here, not a function, but an adder. And my adder is going to internally have the function call operator, and it'll take in a single, well, you know what I'm going to do? It's going to take in an addend. I'm going to call it addend. I'm going to let the adder have a base, built-in base right here. We'll start it off as 0. Oops, not too interesting. Yeah, we'll just say it's 0 by default, right? We'll take in an addend, and then what I'll do here is return the base plus the addend, okay? Semicolon goes here and semicolon goes here, go figure, all right? Now, what error is showing up over here? Oh, no semicolon, gotta have semicolons after structs in C++. Okay, so I have this little adder object here. So if I were to have an adder initialized with a 55, let's say, because that's how we initialize right here, then this is actually going to be some kind of a function that I can call. So not that I would want to, but I could totally do something like this, print adder 55 and 20. Looks a little bizarre, but it should give us 75. Most programming languages are somewhat bizarre. But this would probably be used more like saying this. I would create an adder called add 55, and we'll just call it add 55. And let's print add 55 underscore of 30, and this time we'll get 85. Which we don't, because I wrote this improperly. So yeah, I'm not at 55. This, of course, should be adder 55 like I had before. Right. So this is an adder object taking in 55, and then we can call add 55. Now, the interesting thing is the type of, let's look at the types really fast. The type of add 3 over here is function from int to int. We know that's the case because of the way we passed add 3 into twice. The type of add 5 here, which we could have written auto, I also wrote as function int. Again, we can always write auto if we need to. In case this idea of function int gets really, really complex, you can always in C++, remember, do what's known as a type definition. So if I wanted to abbreviate my work, I could just say that int function could just be an abbreviation for a function that returns an int from an int. And here, oh yeah, you know what, C++, it goes the other way. You have to put your expression first, and then you put the abbreviation after. So if I wanted to, I could replace instances of function int like so with just saying int function, and things will still work. You can find that a nice little abbreviation. So add 3 and add 5 all have the type int function, or function from int to int. But adder right here, or this add 55, this has type adder, which is a little bit different. I can do some interesting things with my adder. I said earlier, would there be a way to chain things together like so? Like, could I make a function called some kind of really cool adder, or just keep adding her? Now we'll just, do we already have a function? We already have a function called that. So let's just call this function sum. Let's call it sum. And we'll try to compute the sum of 1 and 2 and 3 and 4 and 5, which you probably can figure out to be 15. We'll finish it off with something like this, and we'll hope to get 15 somehow. So how do I write a function called sum, which is essentially curried and indefinitely curried, right? Because every time I call sum of something, I want to get back some kind of a function, which I can then call. That will return a function. I call it with another argument. That returns a function, keeps returning a function until I call it with no arguments. And if I call it with no arguments, then I want to just get back an integer. So the way you do that, you have to be, it's going to be the same idea as what I've done with this adder over here. And since I could call this, I guess, a super adder or something, but I think I'll just call it a summer. And the summer is going to have in it two functions. It's going to first have the function call operator, which takes in no arguments and needs to return a single value, the value that we've actually kept in here, right? So we'll keep, not return, but we'll keep in here our current sum so far, let's call it. And we'll start this off at 0. And if we ever invoke our summation with no arguments, like we've done down here, then we'll just return what we've summed up so far. So return sum so far with a semicolon. Now, what about the case where we give our function call operator an argument? We give it a value to add in, an addend, so to speak, right? All right, well, in this case, what do we want to do? Well, we know we want to return another summer, because when you invoke a summer with an argument like so, you're going to keep returning summers until you get to the very end, and you end up returning just a simple integer over here. So what is needed here? Well, let's see. Well, the best thing to do is just return a brand new summer. And that summer will be a struct with a single value called sum so far. And that value will be sum so far plus the addend. And if this is done, we now have a nice little curried summer object. So let's make a summer called sum right now. So we can now print, and let's see if we get a 15 after our 85. And we do. So that's actually, that's fun, and that's pretty cool. Last thing I want to show is a case where these lambda functions, like we have right here, actually are used to modify other data. I mean, I wouldn't recommend it, but just so you can see the C++ syntax for it, I want to show you that one example. So I'm going to make a little function called ring, and this little ring function here is going to, well, I'm going to call it ring times, and then I'm going to say I want to ring a bell, say n times. Okay. So I want to actually ring something n times. Now I'm gonna, this is a very, very contrived example, but it's to show you a little bit of C++ that, you know, this probably isn't used too frequently, but in case you need to use it, you might want to. So I want to count here the number of rings we have so far. We're going to start off with 0 rings so far. And then I'm going to make a little ring function. So we're just going to use auto ring, just don't have to worry about the type. And this is going to be a function whose job it is to increment the number of rings that we have. That's its job right here. Now you can see that we're saying, look, we don't know what rings is because we haven't captured it. So we'll try and capture ring here, but you can see we still have an error. Sorry, rings. We still have an error here, and the error is cannot assign to a variable captured by copy. What does that mean? So we captured rings inside this inner function, inside this lambda, and we captured it by value, meaning that we can only read it. What we want to do is capture it by reference so that we can write to it. So that rings inside of here is actually going to be the field. Okay, we've captured the field. We just actually made a reference to the field. We are talking about this field. Remember, inside an inner function, inside a lambda, in order to use variables captured from the outside, they must be explicitly mentioned here. Or you can just say capture everything by reference that's needed and let C++ figure it out. But again, if you want to be explicit, that's probably a good thing. So if I want to now ring n times, this is really silly, but let's just do it. Let's just go from, let's do a standard little for loop. Things you've probably written a lot before. And we're just going to call this local ring function n times, very, very boring. And then we're going to return the result of rings, just so you can see that the capture was made. So the idea is if I try to ring something 10 times, I should increment this local variable 10 times through an inner function that captured it by reference, and then just return what we got at the end. So hopefully, if I do invoke ring times 10 and print it, you will see the value 10 printed out. And if so, if we get a 10 here without errors, which we do, this is a good place to stop. So by way of a quick review, we saw regular functions in C++, lambda functions, which had captures. We used the operator function call, which helped us do currying, or at least partial application. And we saw that the types of function values were done with that keyword function, that generic type function, which had a function expression that it was parameterized by. And that, in a nutshell, is C++ functions. See ya.